Thank you very much. In this talk, I will describe a theory that I presented here last year, and I claim is a theory that can solve the problems of quantum gravity, both renormalizable and unitary. And I will also explain why I claim it is the right theory of quantum gravity. But most of all, in this talk, with respect to the past year, I will focus more on physical implications and the predictions towards cosmology, because now I want to consider the implications of this theory on cosmology, and cosmology is not my domain, but I'm slowly moving towards that. So we will begin with the Friedman-Robertson-Walker solution, the modifications in this theory, and then the next goal will be inflation, the horizon problem, and other things. So from the point of view of particle physics, high energy physics, the problem of quantum gravity is to make it renormalizable and unitary at the same time. Renormalizability can be achieved by means of higher derivatives. They lead to renormalizability because a higher derivative propagator is better behaved in the ultraviolet. It falls off like 1 over p squared squared, for example. That's enough for quantum gravity. But when you decompose a higher derivative propagator, you will see that it's a difference of poles. So you will have poles with a positive residue and necessarily at least one pole with a negative residue. That violates unitarity if you quantize those poles with the Feynman prescription. We will see that with a new quantization prescription, we will solve this problem. So let's check what unitarity is. Unitarity is a statement about the S matrix, because from high energy physics point of view, we are talking about a scattering theory. And if you decompose the S matrix as 1 plus corrections, 1 plus IT, you can rephrase this identity as the identity for the T matrix written here, which is known as optical theorem. If you use states from your Hilbert space, the same identity can be written in the form you find here, but for the moment, forget about this thing. So the form you find is this one, where you see I just inserted a completeness relation here that is 1, and so you get correctly T dagger T. The point is that you cannot prove this identity from a higher derivative theory because of these minus signs. So you do not prove unitarity, indeed they are not unitary, if you use at least the standard Feynman quantization prescription. What you can prove, however, is called pseudo-unitary equation, which is very similar to what you would like to get. But instead of having a standard completeness relation here, we have some states with a minus sign and some other states with a plus sign. So you can have a plus or a minus. And that is wrong. That is non-unitary, a non-unitary theory. What to do? The optical theorem has a diagrammatic version. You can show this identity for every diagram, basically. The imaginary part of a diagram, for example, the imaginary part of this, is a square integrated on the phase space of final states and sum over all final states, but basically you have a square. So you have positivity conditions. T dagger T is non-negative. And at one loop, for example, if you compute the imaginary part of the bubble diagram, you have a square of the same type of vertex, just rotated. An important thing of this equation is that it is quadratic. Not linear, quadratic. That means that it mixes different loop orders of your expansion. So for example, here you have a tree diagram, here you have a tree diagram, you have a tree diagram, and here you have a one loop. So that tells you that tree level talks with one loop. And you have to be careful to do things and changing your quantization prescription, because you cannot just, for example, throw away some states from your Hilbert space. You can say, let me neglect the unwanted external states. You can do that, but they will reappear in the middle because you cannot choose what appears there. And if they do appear there, you regenerate them back. And therefore, if you really want to throw them away out of your physical spectrum, you have to do something inside your diagrams. Okay, so let's come to the prescription. The propagator is 1 divided by p squared minus m squared. It's ill-defined, and you need a prescription to define it. The Feynman prescription is written here, and it tells you that you add a width, a small infinitesimal width. Why is that okay? That is okay because it satisfies the optical theorem, the first of these two identities. Indeed, if you take that formula for the propagator here, and you take I as a vertex, then you can check this identity, which is the imaginary part of what you get, is non-negative. It's plus pi delta p squared minus m squared, and it is on shell, as you expect. Now, what is a ghost? A ghost is the same propagator with a minus sign in front. That is not okay. A minus sign in front, as you find here, for example, will destroy unitarity, because you will change the sign of the left-hand side. You will not change the sign of the right-hand side because it's a square. So ghosts are these objects. And they violate the optical theorem. However, what I want you to notice is that in this violation, the prescription is crucial, because you have a minus sign here, which violates unitarity, but the delta function comes from the plus I epsilon. So if you touch both, there is hope. You could change the sign here. Both signs would be okay, but the propagators with plus I epsilon and minus I epsilon cannot coexist in the same quantum field theory for reasons that I cannot explain here, but they basically lead to violations of the locality of counter terms and very bad non-local divergences. Those are out of the question. You need something more. Let's see what the answer is. And the answer is what I call a fakeon, namely a fake particle. So basically you do the following thing. You take your propagator and you search for a different prescription, multiply and divide by p squared minus m squared, and you will get this. And I will put also a plus or minus sign in front to tell you, to show you that whatever I'm going to say from now on will be valid with both plus and minus. So it will be okay for both, and then it will help us define higher derivative theories. That's the crucial thing. The sign in front will not matter anymore. So far I've done nothing, but forget about the numerator because it will not matter for the singularity structure of the integrals. Just focus on the denominator. What you have done is to split the poles into pairs. So instead of having two poles there, you have two pairs, and I will now insert a distance between them by means of a weight. So the infinitesimal weight will be here. Okay, so this will be my prescription. This is not the end of the story. This is just the beginning of the story. But the first thing we have to do is to write the propagator this way instead of the Feynman way. Notice that normally Feynman does this. So this is the integration path on the loop energies of your diagram. If you split the poles, then you will have to integrate like that. It's a funny integration path. You will not integrate on Minkowski space. You will have to integrate like that, which is the integral that comes from the rotation of the Euclidean integral. And the rotation, the Wick rotation, however, will not be trivial. First, it is not equivalent to Minkowski because you have a pole in the first quadrant and a pole in the third one. And second, the Wick rotation will not be an analytic operation as it is usually. But that is for later. So a warm-up to suggest that this propagator is not propagating anything is that on shell, when p squared is equal to m squared, for every non-zero width, it is 0. It has no imaginary part. And so the optical theorem will be obeyed with a 0 on the right-hand side. Not plus, which is a particle, not minus, which is a ghost, 0, which is a fake particle. It's something, it's not a 0 in the end, it's really a fake particle in literal sense. However, this story is not that simple. You have to do a little bit more. So let me describe what to do to calculate a bubble diagram where you have two propagators and you have to integrate on the loop energy k0 and the loop space momentum k. What happens? If you integrate on the loop energy by means of this funny integration path, you will have a sum of residues. That's very easy. And you will end up with an expression like that, the integral on the space loop momentum of some integrand. Now, what about the analytic properties of your amplitude? The amplitude is analytic anytime the integrand is non-singular for every k belonging to the domain of integration of k. And the singularities are what's important here. The singularities occur as usual, when the external energy is a sum of frequencies of the internal particles that from virtual become real. The only difference here is that the internal particles have an imaginary part, have imaginary masses. So normally you just have this. This is the normal location of singularities, which is a branch cut here and a branch cut there. What changes when you have a width? That when k spans R3, instead of having two half lines, you fill those two regions. All those regions are locations of singularities for the integrand. Therefore, everywhere inside you violate analyticity, and it turns out that you also violate Lorentz invariance. Why is that? That's not so difficult to understand, because remember that we are integrating on this funny integration path, which is not real. The real integration path is not what we are doing. It has complex contributions. So if you integrate the loop energy on a complex path and the loop space momentum on a real domain, that cannot be Lorentz invariant unless there are miracles and cancellations. However, remember that we have to take epsilon to 0 at some point, and when epsilon goes to 0, the region here, which has a size equal to epsilon, will shrink, and it will reduce to the correct thing you want. So you can say, okay, in the end, I still have two branch cuts. Fine. Now, assume that your Wick rotation from the Euclidean is analytic. What you will get is the analytic continuation from above. That's the Feynman prescription. And the Feynman prescription is what gives you the S matrix, normally. So it's what I call S, or T. S dagger, or T dagger, the complex conjugate, is the anti-Feynman prescription, if you want, the minus I epsilon, and it is what you get if you circumvent those singularities from below. Fine, these are the two options that you know of. But now you see that there is a third option. And the third option is to go inside the region, compute your amplitude there. The result will be not Lorentz invariant and not analytic. And then, from the inside, you take the limit epsilon going to 0, you shrink the region, and in the limit you recover analyticity and Lorentz invariance. However, with some caveats. So that is what you have to do. So you calculate inside, take epsilon to 0, where the region shrinks, and you can prove a mathematical theorem that tells you that the result of what you get when you do this is actually very simple. It's an operation that I call average continuation, and it is exactly the arithmetic average of the two analytic continuations that you obtain from above and from below. It's an unambiguous but non-analytic operation. It's like computing your physical amplitude not from above or from below, but inside your cut. And that will give an analytic function on the cut. And then by analytic continuation, if you want, you can enlarge the cut into cones to make everything more visualizable. What happens? It happens that you will have a different kind of theory with respect to what you always have. Normally you have analyticity. Normally you have an analytic Wick rotation. Here you will have a complex plane, the complex plane of external energies, P0, that's divided into disjoint regions. And above certain thresholds, you will have a different region. You will have a Euclidean region where your amplitude is analytic. You will have a other region where your amplitude is analytic, but the two analytic functions will not be analytically related. However, they will be unambiguously non-analytically related, which means that if you compute your amplitude in the Euclidean region, you will be able to find the amplitudes in every other region by means of this average, but not vice versa. You cannot go backwards. Now we'll see the physical implications of this. First, you have unitarity, because you understand that this kind of prescription is completely symmetric with respect to reflections, with respect to the real axis, and that means that it is real. At the beginning, the propagator was completely real, and by this you keep its reality inside Feynman diagrams, so even the ending result will be real. And if you compute the imaginary part to apply the optical theorem, you will find that the imaginary part is 0. On the other hand, if you want to have the optical theorem, that should be equal to something that cannot be negative. But that something can be 0, because it's a sum on the final states, and it will become 0 if you eliminate those states from your physical Hilbert space, which means that those particles must be projected away. And that means that they will never appear as asymptotic states, which is why I call them fakeons. Actually, there are many other reasons why they call them fakeons, because in many scattering processes, they will fake physical particles in a strictly literal sense. But they will never be, we will never be able to bring them to light, so-called. So from the pseudo-unitarity equation, which we had with a plus or minus 1 there, you get now another equation where, with the new quantization prescription, the coefficients there are not plus or minus 1, but 1 or 0. If you quantize every degree of freedom that had the minus sign in front with a new way. And the zeros can be projected away, so you restrict your Hilbert space, and in the restricted Hilbert space you will have the correct completeness relation. The correct completeness relation, however, will be only in the restricted space.
Diane,
yes.
Can you go back one slide?
Yes.
What happens if in the loop you have a fakeon and a normal particle on the left?
It behaves like two fakeons. Anytime you have at least one fakeon, you will have this.
No imaginary part.
Yeah.
Sorry, but you say that the symmetry up-down is closure, no? Right?
Yes.
So once this interacts with normal particles that have no symmetry, it will lose the symmetry, no?
That is by resumming the perturbative expansion, you can have particles that decay, like the muon, and then it's up to you to talk about unitarity or not. You say that the standard model is unitary. I would say that it is unitary because it is perturbatively unitary, and because you can wait. You cannot wait till the muon decays. That means that you are expanding in the muon width, and therefore you will go back to perturbative unitarity. The point is that the muon can be in the set of asymptotic states. These cannot. So you will never be able to observe them.
What happens if I just take my two derivative theory and apply the same?
Yeah, exactly. Thank you. In a moment, just give me 1 minute, and I will come to that because that's the interesting part. Well, there are many interesting parts, but that's also. So quantum gravity, let's consider the candidate, that's the unique, strictly renormalizable higher derivative theory that you have, which is this one. I added the standard model because you need to have meta for the second part of the discussion. I use redundant constants because I want every term multiplied by different constants, so k squared is like h bar here. But anyway, there are three constants which have to be positive in my case, my theory. This is a higher derivative theory, and if you want, you will have propagators with some wrong signs. Which ones? There is a way to, see which propagators have the wrong sign. For example, you can turn your theory from a higher derivative Lagrangian, which is manifestly renormalizable, to a non-manifestly renormalizable theory by introducing the other degrees of freedom explicitly. So no higher derivatives, but more degrees of freedom. You will have the Hilbert action. You will have the scalar with a potential, with the right sign in front, zeta is positive, and you will have a spin 2 with a complicated action. Forget about this, which is just written. Let's see it here. There is a spin 2 massive field, you know very well, which has a kinetic term, which is a Pauli field Lagrangian, covariantized Pauli field, with the wrong sign. That spin 2 must be quantized as a fakeon. This way we will have both renormalizability and unitarity. Why do we have renormalizability? First, because this theory is renormalizable. Second, because the construction does not spoil renormalizability. Remember that I told you that once you compute everything in the Euclidean region, you have an unambiguous way to compute everything in every other region. So if you renormalize the Euclidean region, sorry, who is speaking?
So you cannot take from Minkowski to Euclidean, but you can do the reverse, from Euclidean to Minkowski. So if I understand, you construct the action.
You cannot work in Minkowski at all. No, in Minkowski it's ill-defined. You will not go anywhere from Minkowski. So since the theory is every region is unambiguously determined by the Euclidean one, once you renormalize that one, the average of two analytic continuations of convergent function will be convergent. But you have a third object, and you asked about two derivative theories. So what about this scalar, which has an action with a positive sign? It can be quantized either as a fakeon or as a physical particle. And this we do not know. You can quantize a normal scalar as a fake particle.
I'm confused. So one over R potential which I derived from gravity, so it's two masses in non-relativistic case. So this graviton could be my physical graviton or it could be fake one.
No, the graviton cannot be fake because it's massless. We will see that only massive fields can be fake. And they have to be heavy.
So, sorry, is there any, so far as understood, there is some kind of ambiguity in quantization?
You have some two possibilities. You can quantize
I call this ambiguity.
mass.
I call this ambiguity. You You don't know how to quantize the theory.
You have two possibilities. Okay, in the standard model, there's some options, some parameters, 20. In quantum gravity, there will be 2 more parameters and this
Okay,
twice possibility. Once you have a finite number of possibilities, I'm happy. Thank you. Now, if you take both theories together, quantum gravity and the standard model, you have this set of fields, and what you add is a triplet with a graviton, the scalar field, which could be fake or not, and a spin 2 massive field, which must be fake. You can ask the same way as Anupam just asked, what about the other ones? Do we know already for sure that they are not fake? I will comment on that in a moment. First, let me stress that this theory is a usual high-energy physics quantum field theory, so you can make your computations as you do in the standard model. Feynman diagrams, widths, loop corrections, resummations of bubble diagrams. You have a triplet, not many fields, 2 new parameters. You can, for example, compute the width of this fake particle. It is negative width because of the minus sign in front of the propagator. And that is a sign of a violation of microcausality. This funny analyticity, region-wise analyticity, has this kind of implication. But this was just to show you that you can make computations, because some people ask me if I can do computations with this theory. And yes, normally there are string theorists who do not believe that you can make computations, maybe, but you can. The projection of these unphysical fields, which are not unphysical, they are fake physical fields, out of the spectrum, is actually a very simple operation. And this I explained just because some people might be puzzled, have been puzzled in some past talks. It's very, very simple. It's like integrating the fakeons out. It's like putting no source, J, for the fake particles. So those particles will remain inside the Feynman diagrams without destroying the unitarity structure. That's the good thing. And they will not be asymptotic states. Equivalently, in your action, you take the fake particle, chi, solve the field equations of that particle with the Fakeon prescription, because there is a unique way to do that. You cannot choose boundary conditions for the Fakeons. You cannot choose initial conditions, positions, velocities. It's blocked. And you insert the solution back into the unprojected action. You will get the projected action. We will see it in a moment more precisely. Because many of the things I told you survive the classical limit, and so we can also start raising some questions that we might even be able to answer. For example, what about the classical action we started with, the higher derivative action? That's not the classical action of my theory, because it contains extra degrees of freedom that should be projected out. So there is a new quantization procedure here. Normally, the starting classical action is the classical action. Here, I call it interim classical action because the classical action will be reached only after the quantization. You go backwards and you classicize your quantum theory, and you will know what to project away and how. So you will have your unprojected field equations for the 3 fields. You will have to solve the equation for the fake field, chi mu or both, and insert the solution into the other equations. That's what you have to do. Let's see what happens in a very simple example. So in the 3 limit, you can skip all the details about the average continuation, about those analyticity properties, because there is no loop integral. And so you can just take the expression I wrote as it is, take the limit epsilon going to 0, and that is a principal value. That is a sum of retarded and advanced potentials, which is the reason why you have.
Then I have a really silly question. So, okay, I can do this prescription, but what would be the Cauchy problem for my fakeon then?
There is no Cauchy problem for your fakeon because you do not have initial conditions. I'm saying your fakeon should be solved with this prescription, period. The Feynman prescription is a way to choose initial conditions, right? And here you have to use this. Let's see in a specific example. Let's start with a toy model, non-relativistic mechanics, mv squared divided by 2 with a force. And you add a higher derivative term. The equations of motions are higher derivative. They factorize two operators. One is the right one you want, and one is the thing you want to turn into a fake. So what you do is to invert that into this with the principal value. So you know how to invert it. And then you get the projected equation. This is the equation in the end. MA is not equal to F, but MA is equal to an average of the external F with an oscillating function. It's very rapidly oscillating. And so that means that to solve this equation, it's not enough to know the external force in the past, but you need to know the external force in a little bit of future. That's why you have a violation of microcausality. But otherwise, this is a Cauchy problem. Well, who asked this? I don't know. This is a Cauchy problem, but not for the fake part. Fake part disappeared and it originated this non-local average. It's like saying that everything is fluctuating everywhere, but so tiny, let's say 10 to the minus 36 seconds, that's out of reach for our. It is 1 divided by the mass of the fake particle. If the mass of the fake particle is 10 to the 12 GeV, it would be 10 to the minus 36 seconds. And we cannot measure time precisely, more precisely than the attosecond, which is 10 to the minus 18 today.
Will it have impact on equivalence principle?
I've been asked that question, and I'm not sure I can answer right away, but the person who asked me elaborated on that, and he concluded that yes, it will have an impact, but I cannot tell you why, how now. It's one of the things in the list. So let's come to the final comment on something that you might find more interesting, the Friedmann-Robinson-Walker metric, how the projection works in the classical limit. So the Friedmann-Robinson-Walker metric starts from this ansatz, and out of the triplet, the spin 2 will be insensitive to this ansatz. So basically you have r plus r squared only, the Starobinsky action. And since chi mu nu has to be fake and it is absent in this discussion, and phi can be both, to make this interesting, I will treat phi as a fake and see and illustrate what happens. So if you start from the higher derivative theory and you work out the field equations, the equations of motion, here they are. Maybe I didn't find in the literature the equations written in such a nice way, so maybe you find this useful also for your own purposes. The factorization you see here, I didn't find in the literature. You factorize this thing times an operator, you factorize this thing times the other operator, which are defined here. And forget about the equation for phi, it's not important here. The factorization allows us to make the projection easy, because you take this operator and you invert it. Like here, you see you have a factorization, you take the operator and you invert it with the Fakeon prescription. And so the projected equations here look like this. They look like the normal Friedmann equations where on the right-hand side, instead of having rho and p, you have averages. And the averages are calculated with this prescription, which is retarded and advanced. So it's like the average of the force. Now, or if you want, you can define a certain transformation on rho and p that make the equations look exactly like the usual ones, but they are not, because these are rho tilde and p tilde. So there is something inside, and the average depends on A, because the average contains the operator sigma, and sigma contains A. Yes, thank you. I think I'm over, almost. There is one case where you can solve the projected equation exactly. There are two cases. One is radiation, one is the vacuum energy density, and the third is the combination of the two. Combination of radiation and vacuum energy density can be described by this equation of state, and just show you the solution. If anybody is interested, you can check my papers to.
So what happens in antidesit when we get close to singularity? We take negative vacuum energy plus radiation. The entropy goes up. Normally there is a singularity. Here what happens?
I think it is encoded into this solution, but I didn't check that. But this is the exact solution. What I want to point out here is that this is a lucky situation where you can solve the equations, the projected equations, but in the general situation, the projection is not over. Why? Because you will find something upsetting maybe here, but basically the entire construction, the Fakeon prescription, is defined from quantum gravity. Quantum gravity is perturbatively defined. The projection is perturbatively defined. And since the classical equations only follow from the projection, the classical equations themselves are only defined perturbatively. So basically, in writing the equations, you will have the same problems that you normally have in quantum field theory. You run into asymptotic series. The equations are defined perturbatively, and just to write down the equations, projected equations, the classical projected equations, you will run into non-perturbative effects, basically, even at the classical level. And already dust is a too difficult problem of that kind, or any other situation. So let me conclude. Oh, I had another comment on what Anupam raised. What about the other fields of the standard model? Are they fake or not? There is a possibility that the Higgs boson is fake. I pointed out this in a recent paper. Data are not enough to exclude it because, okay, I have to skip this. If you want, we can discuss later. Conclusions. This theory is as close to the standard model, is the closest proposal for quantum gravity, closest to the standard model, and it admits a perturbative expansion in terms of Feynman diagrams. You can make calculations with a comparable effort. It can be coupled to the standard model itself straightforwardly, and it could be the most predictive theory ever, because with 3 parameters and perturbation theory, you can cover from astronomical distances far below the Planck length. The other approaches that you are aware of have difficulties in predicting string theory. They have difficulties even in their own definitions, look quantum gravity, or they rely on non-perturbative methods and dualities. So I think that this is far superior to every other proposal. Thank you very much.
Thank you. Questions? Okay.
Well, you coupled with the standard model, but we know that the standard model have spontaneous symmetry breaking. And spontaneous symmetry breaking generates a cosmological constant. That means that you are in the de Sitter space, and the de Sitter space is not the same than expanding on a flat background. So I don't think these considerations are actually possible in the case of coupling with the standard model.
I agree with that. You have the cosmological constant even without the standard model. Just these extra terms generate by renormalization a non-trivial cosmological constant. So the question is there unitarity in a strict sense when there is a cosmological constant? Now that depends on the infrared value of the cosmological constant. Actually, the far infrared value it doesn't depend on the value we measure. And there is still the possibility, if you check the renormalization group equations, that that value is 0. But even if not, you might have a tiny violation of unitarity at large distances. But you will, it's like an anomaly if you want, right? But there is still a possibility that, strictly speaking, the cosmological constant in the mathematical sense goes to 0 in the far infrared. But there is no far infrared in a scattering process, right? So
it might go, but then you added the dark energy. Dark energy is again a cosmological constant.
Yeah.
So you are back to the problem. So quantization in the Sitter space is not the same.
I didn't add dark energy. I just studied a toy model with dark energy.
So at some point you said that, if I understood correctly, that your prescription is equivalent to integrate out the field, the fakeon.
The projection is integrating out. The prescription leads to the projection. If you do not quantize with this prescription, you cannot project. Projection is integrating out.
Okay, so it's not, if I integrate out the field without the source, I do not get all your prescriptions.
No.
Okay.
You need first to no.
So mechanically you are working on a reduced Hilbert space, and then you are deriving a classical mechanics for that. So at some point you said you are averaging over, in the classical system you are averaging over, but what exactly you are averaging over? Like quantum mechanically I can think about like averaging over some states.
Here you are averaging over your force. So to write down the classical field.
Force or your phase space now?
No. There is no phase space. You are in a classical environment. You have F equal ma. You need to know a force. I'm telling you that you have to average that force in a little bit of future, 10 to the minus 36 seconds, to predict the far future. So there is an extra uncertainty, classical uncertainty, even with h bar equals 0 in every prediction.
If you complete the scattering negated by particle for the relative, this is very badly infrared divergent.
Is
That's momentum.
why infrared divergence? Ultraviolet.
Infrared, no? 1 over p to the fourth at the small p, which is very, very big.
I don't have 1 over p to the fourth. These are massive. These are massive.
No. So if you go to energies much above the mass, then you get power like infrared divergences.
No, the infrared is Einstein gravity.
We are already out of time. And the last question, Alex.
Okay, you said that, and my feeling is that this is one of your main statements, is that fakeons are not, that the fakeon is not a synthetic state.
Yes.
Okay, but okay, any real unstable particle is not an asymptotic state. So my question